In this movie, I'm going to bring together everything that we've seen so far about vectors and quaternions, combining them together into a single complete package and achieve more sophisticated functionality. In particular, I have this scene in front of me here, which you can find under the Scenes folder and Orbiting folder, and you'll find the orbiting scene as well as the orbiter script. This script has been attached to the object here called Orbiter. Now we have two objects in the scene. We have the pivot point, which is this caret object. That's going to do absolutely nothing at all but just sit there. And then we have the orbiter object, which is this cube here, and it has the orbiter script attached. This script has primarily two properties, or rather three properties. It has a pivot point. This defines the caret object in the scene. It has a pivot distance. This is the amount of space between the caret and the cube which should be maintained constantly. And then we have the rotation speed. What we can do is use the up and down and left and right keys on our keyboard to continually orbit this cube, rotating it around this caret point. So to see this in action, I'm going to press play on the toolbar here, and we can see that the cube snaps into place around this caret. And if I use the left and right arrows, you can see that the cube is constantly orbiting this caret object. Notice that this cube is not a child of the parent object, so we are not achieving this kind of behavior using parent and child relationships. This is being created entirely in code using quaternions. We can use the left and right arrows on the keyboard to rotate this object around the caret. I can also use the up and down keys to rotate around the caret as well. So I can create this complete orbit rotation around the caret. And notice that this cube, as it rotates around the caret, it's constantly turning and it's constantly facing the center of rotation. So we can have this ability to rotate all around this caret entirely like this. So I'm going to press stop on the toolbar here and take a look at the MonoDevelop at the code that we are using to achieve this. That is the code included inside the orbiter script here. So I'm going to bring in MonoDevelop into our view here and take a look at class orbiter, which again derives from mono behavior. We have several properties included in this script. We have the pivot object, the object around which we should rotate. We have the transform component of this object, and we have a quaternion that we are using as an intermediary quaternion. This is going to be our destination that the cube should always be reaching. Notice that this is set the initial value of quaternion.identity, which is a constant value. Quaternion.identity simply means 0, 0, 0 rotation on the X and Y axis. So in other words, no rotation at all. That represents the quaternion identity. In the awake function, as we see here, nothing special at all. We're simply getting the transform component on the cube object. But the update function is where the magic happens. We are using the cross-platform input manager getAxis horizontal and getAxis vertical to read input data from the keyboard. So the horizontal axis refers to the left and the right keys, or the A and the D keys on the keyboard. When the player is pressing the left key, horizontal will be -1. When the player is pressing the right key, horizontal will be +1. If the player is pressing nothing, horizontal will be 0. And if the player is doing something totally crazy, like pressing the left and the right keys at the same time, the value will also be 0 because -1 + 1 = 0. And again, a similar thing is happening for the vertical, except this maps to the up and down arrows and to the left and right arrows on the keyboard. Again, in order to use this cross-platform input manager, it is important at the top of your source file that you also include using standard assets.cross-platform input. It is important that you have that line specified, otherwise you cannot use this cross-platform input manager. Again, to use the cross-platform input manager as well, you have to import the cross-platform input manager package. You can easily do that by going back to Unity and choosing Assets, Import Package, and then choosing Cross-Platform Input. This is a native package that ships with Unity. So I'm going to go back to MonoDevelop here and take a look again at the update function. What we are doing here is we are specifying these values rot x and rot y. This calculates the amount of angle rotation on the x and the y axis that we should be using. So this accumulates over time. So rot x is going to be equal to the rotation speed multiplied by time.delta time multiplied by the vertical value. Remember, if we're pressing nothing, vert will be 0, in which case anything multiplied by 0 will equal 0. Notice we're using plus equals to accumulate those values. So in the cases where we're pressing nothing, nothing is going to be added. That's absolutely fine because it shouldn't change the rotation at all if we're pressing nothing. These two rotation values, the rotation on x and the rotation on y, which are measured in degrees, are then being used in the lines succeeding this to construct quaternions using the quaternion.Euler function. So we're first constructing the amount of rotation we should use on the y-axis. Quaternion.Euler, 0 on x, 0 on z, but here we're specifying the y rotation, and this is being stored inside an intermediary quaternion called y-rot. In the next line, we are then combining together the two rotations, y-rot multiplied by the rotation around the x-axis. And it's worth mentioning here that quaternion multiplication is not commutative. What that means is the order in which you multiply matters. That might seem ridiculous because, of course, 2 times 5 is the same as 5 times 2. It doesn't seem to matter which order you do it in. A times B is the same as B times A, but in the world of quaternions, this is not the case. A times B does not necessarily give you the same result as B times A, so it's important to be aware that the order of multiplication with quaternions matters. In this case, I'm rotating first around y, and then I'm rotating around x. In the next statement here, what I am doing is I'm specifying the rotation of the cube object. This will ensure that the cube is facing in the right direction. But there's still a problem that needs to be addressed, because although we want to rotate the cube around the pivot point, it should also maintain the distance from that pivot point, and that is what this line is doing. We are adjusting not just the position here, but we are adjusting the rotation and the position combined. So here we have the pivot point position plus the rotation of this cube around that center point multiplied by the forward vector multiplied by the pivot distance. We are rotating that cube around the pivot point, and then based on its forward vector, we are multiplying it by the negative pivot distance to move that cube in reverse away from the pivot point, offsetting it away to ensure that it maintains that pivot distance. So I'm going to go back to Unity here and press play, and you can see that what's happening is, as I press left and right on the keyboard, what actually happens is this cube begins at the same position as this caret. It's first rotated, and then we take its forward vector and multiply it by the negative distance, the pivot distance, to move it back into the position where it is as it orbits around this caret. So that's the way that we achieve orbiting in Unity using a combination of vector arithmetic combined with quaternion multiplication. And in doing this, you should now be able to create pretty much any object that can rotate to face any other destination and can orbit around any other object. That completes the first module of this course. This has been 3D Motive. My name's Alan Thorne. I hope you found this helpful, and I can't wait to get started on all the material that's going to be in the succeeding part.